Hello and welcome back to the Master of Civil Engineering. In this video, you will learn that how to design a concrete mix using the ACI Code 211. In this video, we will be designing a green concrete. Okay, we will be learning a full process of how to design a concrete mix using the ACI Code. I have been given a question which states that given reinforced slabs of a hotel near Burj Al Arab, Dubai, the reinforcement consists of 8 number bars with 150 mm center to center spacing, rebar cover is 30 mm and the slab thickness is 200 mm. No exposure conditions are needed. We have to find the weight of water, cement, coarse aggregate, fine aggregates, and we have to consider ground granulated blast furnace slag for designing a green concrete mix. Okay, you can see the material properties. Okay, for our concrete mix, we have aggregates, coarse aggregate in the size range of 20 to 10 mm and 10 to 5 mm. Fine aggregates in the size range of 5 to 0 mm and 0.6 to 0 mm. Okay, you can see the specific gravity, moisture content, absorption and rodded unit weight of coarse aggregate given already. Specific gravity of our Portland cement is 3.15 and GGBS is 2.9. You can see the gradation details for our coarse and fine aggregates. Okay, this is the percentage passing and this is the sieve size in mm. For our concrete mix, we have to design a concrete mix having cube compressive strength of 25 megapascal, and we have to use the GGBS of cementitious material about 40%. We have to prepare 3 types of concrete specimens, 4 cubes, okay, 150 mm. Testing at 14 days for compression and non-destructive testing, and 2 specimens at 28 days for compression, 2 cylinders 200 mm height and 100 mm diameter. One is tested at 28 days for compression and one is tested at 28 days for indirect tensile strength, and one beam, okay, 100 mm into 100 mm into 500 mm length, and we have to test it at 28 days for flexural strength. Okay, the first thing which you will do is first you will learn what is a green concrete. Okay, so green concrete, this is defined as a concrete which uses waste material such as fly ash or GGBS as one of its component. Okay, and its production process does not lead to environmental destruction, and it has high performance and life cycle sustainability. Okay, and structures considered constructed with green concrete, they have comparatively less life than structures constructed with conventional concrete, but they are more economical. Okay, the first thing which you will do is that you will blend the aggregates to get the required gradation. Okay, first we will take the coarse aggregate. So I have 2 types of coarse aggregate, 20 to 10 mm, okay, and 10 to 5 mm, and I have to blend them to get these specifications. Okay, so I will blend, that is, I will take 40% of coarse aggregate A and 60% of coarse aggregate B and mix them to get the this specification, to get this gradation. My gradation should be in this range. Okay, so 25, it will be 0.4 into 100 plus 0.6 into 100, which is 100. It is in the range of 90 to 100. Similarly for 14, you will 14 mmc, you will take 0.4 into 22 plus 0.6 into 100, which is 68.8, and it's again in the range 40 to 80. Similarly for 10 5 mmc, you will take 40% of coarse aggregate in the range of 20 to 10 mm and 60% in the range of 10 to 5 mm, and you will get the required gradation. Your gradation will meet these specifications. Okay, that is, for 10 mm our gradation should be in the range of 30 to 60. You can see it's 53.8, and for 5 mm it should be 0 to 10, and it is 4.8. okay, it's in the range. Okay, so this is how you will blend the aggregate. You have to blend it according to your aggregate size, okay, percentage passing, to get the required gradation which is within the specification limit. Okay, so after blending these aggregates, now you have to find the combined properties of this coarse aggregate. So blended specific gravity of the coarse aggregate, okay, it will be G is equal to 1 divided by P1 divided by G1 plus P2 divided by G2, that is 1 divided by percentage. We have taken 40% for this 20 to 10 mm, so it will be 0.4 its specific gravity is 2.71, and for 10 to 5 mm we had taken 60%, so it will be 0.6 divided by 2.7, which is equal to 2.704 is our blended specific gravity. Similarly, blended percentage absorption, it will be 0.4 into 0.4 plus 0.6 into 0.6, which is 0.52%. okay, and moisture content, this will be 0.4 into 0 plus 0.6 into 0, which is 0%. okay, so moisture content for these aggregates will be 0%. After that, you will blend the fine aggregates to get the required specification. okay, and this time you will take 5 to 0 mm 50% and 0.6 to 0 mm 50% to get the required specification gradation within the specification limit. okay, so if I take my fine aggregate starts from this, that is 2.36 to 0.075, so 0.5 into 40 plus 0.5 into 100, this is 70, it's within the specification limit. Similarly, 0.5 into 25 plus 0.5 into 100, it is 62.5, which is again in the limit. Similarly, 0.5 into 10, 0.5 into 46 is 28, which is again in the limit. okay, and so on for this 150 mm cement, 75 micron sieve. okay, similarly, simply you have to mix that is 50% of this 5 to 0 mm and 50% of this 0.6 to 0 mm to get this blended aggregate. okay, which whose limit is within the specification limit. okay, again you have to find the properties of the blended fine aggregate. So blended specific gravity of fine aggregates, this is 1 divided by 0.5 divided by 2.68, which is the specific gravity for 5 to 0 mm, plus 0.5 divided by 2.63, which is the specific gravity of 0.6 to 0 mm. okay, so blended specific gravity for fine aggregates is 2.655. After that, moisture content, this is 0.5 into 0.4 plus 0.5 into 0.8, which is 0.6%. absorption, this is 0.5 into 0.8, okay, which is the percentage absorption for 5 to 0 mm, plus 0.5 into 1.2, which is the percentage absorption for 0.6 to 0 mm. So blended percentage absorption is 1% for fine aggregates. After that, after getting the blended properties, you can combine both of these, that is coarse aggregate and fine aggregates, and make a table. Now this is the percentage passing. okay, our size starts from 37.5 mm and last is 75 micron. We already know the percentage passing. You can find the percentage retained by 100 minus percentage passing. So 100 minus 0 is 100 for 5 mm sieve. For 10 mm sieve, 100 minus 98.5 is 1.5, 100 minus 36.5 is 63.5, and so on for the rest of the sieves. And after that, you have to find the fineness modulus of the fine aggregates. okay, so fineness modulus of fine aggregate, this is the summation of percentage retained on 4.75 mm sieve, 2.36 mm sieve, 1.18, 0.6, 0.3 and 0.15. okay, our sieve ranges from 2.36 to 0.15, so we'll take the summation of 30 plus 37.5 plus 43 plus 72 plus 96.5 divided by 100. So we will get the fineness modulus equal to 2.8. This is the fineness modulus of the fine aggregates. okay, now we will come to the specifications. okay, so first we need to know the average compressive strength for our specimen. Already we have been given that cube compressive strength is 25 megapascal. Our number of testing specimens, that is 4 cubes, 2 cylinders and 1 beam, this is equal to 7, which is less than 15. Since we don't have any data for the standard deviation, okay, so we will use the ACI code table, that is adjustment for the small number of samples. Our samples are less than 15, so additive factor based on this cube compressive strength, when the specified strength is less than 21, required average compressive strength is FC dash plus 7 megapascal. okay, and when it's 21 to 35 it's fc dash plus 8.5, and when greater than 35 it's fc dash plus 10. Since our cube compressive strength is between 21 to 35, so required average compressive strength will be fc dash plus 8.5, so it will be 25 plus 8.5, which is equal to 33.5 megapascal is our required average compressive strength. Okay, and now nominal maximum aggregate size. Okay, so our slab thickness is 200 mm, reinforcement spacing is 150 mm, and rebar cover is 30 mm. We will use the again ACI specifications. So a maximum aggregate size from form dimension, this is 1/5 of the minimum clear distance, so it will be 1/5 of the 200 mm, which is the slab thickness. It's 40 mm. For reinforcement clearance condition, it will be 3/4 into 150 mm, that is 3/4 of the minimum clear space between the reinforcement, which is 150 mm. So it is 112 mm, 112.5 mm. For reinforcement clearance condition, it is 3/4 into minimum clear space, which is 30 mm, so it's 22.5 mm. We have to take the least one, so least one is 22.5 mm, so maximum aggregate size for our concrete is 22.5 mm, but we have to find the nominal maximum aggregate size. Maximum aggregate size is the smallest sieve through which 100% of the sample must pass, and nominal maximum aggregate size is the smallest sieve through which majority of the sample passes, that is only up to 15% can be retained. So nominal maximum aggregate size is we will take it as 19 mm. Okay, let's take it as 19 mm. After that you have to find the air content requirement for our concrete. Okay, you can see the table. Since our concrete is non-air entrained concrete, okay, and you can see the different air content for different nominal maximum aggregate size. Our maximum aggregate size is nominal maximum aggregate size is 19 mm, and we are using the non-air entrained concrete, so our air content will be 2%. Okay, that is for 19 mm and non-air entrained concrete, it's 2%. You can find these tables in the ACI code 211. Okay, after that we have to find the slump for our concrete, so we have to find the workability requirement. So for slabs you can see that maximum slump is 75 mm and minimum slump is 25 mm. So let's, for our concrete, let's take a slump of 50 mm. Okay, that is in between 75 to 25 mm. After that you have to find a water cement ratio. Okay, since for our concrete no relationship between compressive strength and water cement ratio has been given in the question, we will use the ACI table to find the relation to find the water cement ratio. Okay, so this table gives me the water cement ratio and the versus compressive strength for non-air entrained concrete and air entrained concrete. Okay, in our question no exposure conditions is specified. It means we are free to choose the water cement ratio as long it provides the desired workability and strength, but we have to prepare the concrete of required strength 33.5 megapascal. We will use this ACI table of 28-day compressive strength versus water cement ratio. So for 34.5 megapascal for non-air entrained concrete, water cement ratio is 0.48, and for 27.6 megapascal compressive strength for non-air entrained concrete, water cement ratio is 0.57. We have to interpolate between these two values for 33.5 megapascal. So from interpolating between 27.6 and 34.5, we will get the water cement ratio equal to 0.49. Okay, now after finding the specification we will proportion our mixture. Okay, so first you will find the coarse aggregate bulk volume. We have been given the rodded unit weight of coarse aggregate as 1.57 megagram per meter cube. It means it's equal to 157 kg per meter cube. Okay, we will use this table of ACI, that is bulk volume of coarse aggregate per unit volume of concrete, and you can see here is the nominal maximum size of aggregate and In here are the columns for bulk volume of dry rodded coarse aggregate per unit volume of concrete for different fine name modulus of fine aggregates. Okay, our nominal maximum aggregate size is 19 and fineness modulus of fine aggregates is 2.8. So it means that 0.62 of the bulk volume of the concrete will be coarse aggregate. Okay, so 0.62 of this rodded unit weight will be coarse aggregate. So mass of coarse aggregate is equal to 0.62 into 1570, which is equal to 973.4 kg per meter cube is the mass of coarse aggregate. Okay, after that, water content, we have to find the water content. So for non-air entrained concrete having slump of 25 to 50 nm and nominal maximum aggregate size of 19 mm, we will use the table of ACI, which is the approximate mixing water in kg per meter cube for different slumps and nominal maximum aggregate size. Our slump is 25 to 50 mm and nominal maximum aggregate size is 19 mm. So it means the approximate mixing water for our concrete is 190 kg per meter cube. Okay, so required water is 190 kg per meter cube. This table is for the angular aggregates. If you have other types of aggregate shapes such as subangular, gravel or round gravel, you have to reduce the water content accordingly. Okay, you can see this table when aggregate shape is different than angular. Since our aggregate shape is angular, so we don't have to reduce the water content. After that, cement contents, we know that water cement ratio is weight of water divided by weight of cement. So weight of cement will be weight of water divided by water cement ratio. Weight of water is 190 and water cement ratio, we already found it, it's 0.49. It means the weight of cement, this is 388 kg per meter cube. This is the cement required for our concrete mix. Okay, we can see the minimum requirement of cementing material for concrete used in flat work. Okay, so for nominal maximum aggregate size of 19 mm, cement content, minimum cement content required is 320 kg per meter cube. Since we are taking the cement content equal to 388 kg per meter cube, therefore it's okay. Okay, weight of cement is 388 kg per meter cube, but we have to use 40% ground granulated blast furnace slag. So 40% of 388 is 155 kg per meter cube. So weight of ordinary Portland cement required is 388 minus 155, which is 233 kg per meter cube. Okay, so weight of Portland cement is 233 kg per meter cube and weight of GGBS is 155 kg per meter cube. Okay, total is equal to 388 kg per meter cube. After that, fine aggregate bulk volume, we will assume the concrete volume. Let's take concrete volume of 1 meter cube and we will use the absolute volume principle. So weight of water is 190 kg for 1 meter cube. We have to use the weight of water 190 kg. Density of water is 100 kg per meter cube. It means the volume of water will be 190 divided by 1000, which is 0.19 cubic meter. Weight of cement is 233 kg. Weight of cement required for 1 meter cube is 233 kg. Specific gravity is 3.15. So volume of cement, this is weight of cement divided by specific gravity multiplied by the density of this water. So it will be equal to 0.074 cubic meter. Weight of GGBS required for 1 cubic meter is 155. So volume will be weight divided by the specific gravity multiplied by the density of water, which is 0.053 cubic meter. Air content for our concrete is 2%, so it is 0.02 cubic meter will be the volume of the air in our concrete. Similarly, weight of coarse aggregate is 973.4 kg. Specific gravity, blended specific gravity for a coarse aggregate is 2.704. So volume of coarse aggregate will be 973.4 divided by the specific gravity multiplied by the density of water, which is 0.36 cubic meter. By absolute volume principle, volume of fine aggregates, this will be equal total volume of concrete, which is 1 cubic meter minus volume of water, volume of cement, volume of GGBS, minus volume of air, minus volume of coarse aggregate. So it's equal to 0.303 cubic meter will be the volume of fine aggregates for 1 cubic meter in our concrete. Weight of fine aggregates will be volume of fine aggregates multiplied by the specific gravity of fine aggregates multiplied by the density of water. Volume is 0.303. Blended specific gravity of fine aggregates is 2.655 multiplied by the density of water, which is 1000. So weight of fine aggregates for 1 cubic meter is 804.47 kg. Okay. After finding the weights, now we have to apply the moisture corrections because we are assuming the saturated surface dry condition for aggregates. So mass with moisture, it will be the dry mass of aggregate into 1 plus moisture content in the aggregates, and free moisture mass, that is free water available, which is from the aggregates, it will be the dry mass multiplied by the moisture content of aggregates minus absorption of aggregates. You can see the table. So for coarse aggregate, dry mass is 973.4, absorption is 0.52, and moisture content is 0. Mass with moisture, it will be dry mass, that is 973.4 multiplied by 1 plus moisture content, so it will be 1 plus 0, which is 973.4. Free mass, it will be dry mass, that is 973.4 multiplied by 0.52 divided by 100. We have to since this is a percentage, minus 0 divided by 100. So free moisture mass in kg from the coarse aggregate is minus 5.0 kg. It means these coarse aggregates are taking water from our concrete. We have to add this much extra water for the coarse aggregates. Similarly, for fine aggregates, dry mass is 804.47, absorption is 1%, and moisture content is 0.6%. So mass with moisture will be 804.47 multiplied by 1 plus moisture content, so 1 plus 0.6 divided by 100, which is 809.3 kg. Okay, this is kg, not lib, sorry. And free moisture mass, this will be dry mass, that is 804.47 multiplied by moisture content, which is 0.6 divided by 100, minus absorption, which is 1 divided by 100, so it will be minus 3.22 kg. Again, fine aggregates are also taking water from our concrete mix. We have to add this much extra water for the fine aggregates. So total excess moisture which we have to add to our concrete is 8.28. If it was a plus sign, then we have to reduce this much amount of water from our water, because aggregates were providing this much amount of water. But since it is negative, it means we have to add this to the total water required. Total water required is 190 kg for per cubic meter. We have to add this much. This is 8.28. So total water required is 198.28 kg. Okay. So ingredients required for 1 cubic meter of our PCC, water is 198.28 kg, cement is 233 kg, GGBS is 155 kg, fine aggregates is 809.3 kg, and coarse aggregates is 973.4 kg. Now we will use the batching. We will use the way batching because it's more aggregate. So we have to prepare the concrete equal total volume of specimens, and we will take 20% extra for losses. Okay, so total volume of specimen is volume of cubes, volume of cylinders plus volume of beam. We are using 4 cubes, so 4 into 150 mm, which is 0.15 cube. Cylinders, 2 cylinders, 2 into pi d square, d is 100 mm, and height of the cylinder is 200 mm or 0.2, and volume of beam is 100 mm into 100 mm into 500 mm, so 0.1 square into 0.5. So total volume for our specimen is 0.0216 cubic meter. Total volume of concrete is 1.2 multiplied by 0.0216 because we are taking 20% extra for losses. So total volume of concrete is 0.026 cubic meter. Okay. Now weight of water required for 1 cubic meter is 198.28 kg. So for 0.026 cubic meter, it will be 198.28, which is 5.2 kg. Similarly, weight of cement 233 into 0.026, which is 6.1 kg. Weight of GGBS 155 into 0.026, which is 4.03 kg. Weight of coarse aggregate 973.4 into 0.026, which is 25.31 kg. And weight of fine aggregates 809.3 0.3 multiplied by 0.026, which is 21.04 kg. Okay, so you can see the final ingredients required for our 0.026, sorry, this is 0.026 cubic meter of concrete. So weight of water required is 5.2 kg, weight of cement required is 6.1 kg, weight of GGBS is 4.03 kg. Fine aggregates total required is 21.04 for 5 to 0 mm. Since this is 50%, so it is 0.5 into 21.04, so it's 10.52 kg. 0.6 to 0 mm is again 50%, so 0.5 into 21.04, this is 10.52 kg. Coarse aggregate total weight is 25.31 kg. For 20 to 10 mm, this is 40%, we have taken 40% this, so 0.4 into 25.31, which is 10.12 kg, and 10 to 5 mm we have taken this 60%, so 0.6 into 25.31, which is 15.19 kg. Okay, so this is how you can design a concrete mix using an ACI code. I have given you full procedure. Okay, that is finding first the specification and then proportioning your mixture. I hope this solution video was clear and effective. If you still have doubts, you can write them in the comment box. Okay, I will be happy to answer this. Okay, and if you find this video helpful, please subscribe to my channel and share this video with your friends. Thanks for watching and stay tuned.